Today we're going to begin our unit on reaction rates. We're going to start by looking at what's called the collision model. Reactions occur during molecular collisions. The particles actually have to collide and meet each other, and that helps to explain some different characteristics about chemical reactions. If we look at this equation here, we have a molecule BrNO, and when it collides with another one of itself, it forms Br2 and two NOs. And what has to happen is these need to collide properly. In fact, the two BRs must hit each other in order for this reaction to take place. So the BR and the BR have to collide. If the BR of the BrNO collides with the O of another BrNO, no reaction is going to take place. So there is a proper orientation that needs to happen in order for a reaction to occur. There are some conditions that we can look at that affect reaction rates. The first one is what's referred to as the nature of the reactants. It says substances vary greatly in their tendency to react depending on their bond strength and structures. This has to do with how they react, just the basic chemistry involved with things reacting. Certain chemicals will not react. They're just inert with each other. So we have to take into account what actually we are trying to react together. And then some more basic factors. Once we have things that actually will react together, we want to look at the concentration. So concentration, the rate of the reaction depends on the number of collisions that occur between the reactants. If we increase the concentration, the rate of the reaction will increase. For a gas, we can increase the pressure, because by increasing the pressure, we're going to decrease the volume, and by decreasing the volume, we are therefore increasing the concentration. Temperature is another condition that affects reaction rate. Because temperature is a measure of average kinetic energy, increased temperature will accelerate reactant speeds and thus increase the number of high energy collisions. So it's not good enough for molecules just to collide. They need to collide with a certain amount of energy that will make them react and form products. And finally, surface area. For a heterogeneous reaction, especially where we have mixed states, reaction rates will increase with increased surface area. This graph is really, really important, and you should definitely make sure you have it in your notes. The reaction above is the reaction that this is a graph of. If we look right here, we have our reactants. And this is the potential energy of the reactants. And if we look here, we have our products. And this is the energy of our products. What has to happen is the methane and the oxygen need to combine, and they reach what's called an activated complex. So they have to go up in energy. So they have to have a certain amount of energy, more than what they have to react. And then once the reaction takes place, it's favorable. So this drops lower. This change here, that we're looking at, this is the energy of the reaction that we learned when we did our unit on heat. Because my reactants are higher than energy than my products, that means that this is an exothermic reaction. So my energy is with the products because they're lower in energy. If this was an endothermic reaction, this line here, this would be up here. So this would go up and go to here, and my energy of my products would be higher than my energy of my reactants. But that would be for an endothermic reaction. This energy here, if we look from here to here, from the top to the point of where my reactants are, this is the activation energy, and this is the minimum energy needed for a reaction to occur. So if I have molecules collide, they might not have enough energy to react and form products. So as we said, the activation energy is the minimum energy needed for a reaction to occur. And if you noticed at the top of the point, there was something called an activated complex. This is a short-lived and unstable intermediate that occurs at the height of the activation energy. It's neither a reactant nor a product, but sort of a weird go-between as the reaction is taking place. So if the molecules are joined but haven't quite reformed into the products, this is this activated complex. Either there'll be enough energy to proceed to products, or it'll become an activated complex and it can go back down into reactants if there isn't sufficient energy. A catalyst is something that speeds up a reaction without being consumed. So a catalyst is something we add to a reaction, but it's not a reactant and it's not a product. It's just something that facilitates the joining of the reactants to form products. A biological catalyst, a catalyst that we have in our body, is called an enzyme. And you'll learn a lot about those when you go to biology. So a catalyzed pathway, a catalyst works by lowering, it makes it easier. So this is my catalyzed pathway, okay? What this means is a catalyst lowers this activation energy. It works, I like to think of it like a magnet. It works to help maybe bring the molecules together or bring them together with the proper orientation so that they can join and go ahead and make products. But this catalyst is not used up. It's not consumed in any way. It's not added in. It's not balanced into the reaction in any way. But all it does is it helps these react, and by doing so it lowers the activation energy, and that's the big part of a catalyst. And then a heterogeneous reaction, these are just sort of defining two terms that we already know and then applying it to reactions. A homogeneous reaction is reactions involving one phase. We've done homogeneous, we've done both types of reactions, we've just never categorized them. So something that's a reaction that's all gases, like we did in gas laws, or all aqueous, like we did in our solution reactions. Those are homogeneous reactions. Heterogeneous reactions are reactions involving at least two phases. So something like zinc metal plus aqueous hydrochloric acid. That would be a heterogeneous reaction.